What's going on, everybody? This video we're going to look at related rates. We've got, I think, 5 examples to work. So let's go ahead and get started. So let's just take a quick look at this first steps for solving related rates problems. And students tend to struggle with it a little bit, but it's not that difficult to do. So the steps for solving related rates problems: identify the variables and the rates in the problem. If possible, make a sketch showing the variables. Now, you won't be able to draw a sketch every time, but if you can, do it. Determine the equation relating the variables. Now, some of the related rate problems are nice because they give you the equation. And that's nice when they do that. And I think the first 2 examples we worked, they're giving us the equation. I know in the first example they do. You can see it right here. But the difficult part about these problems is actually finding the equation when they don't give it to you. And we've got some examples of those. Differentiate with respect to time, and then solve the required rate. All right, so let's get started, and hopefully after you watch the video, you'll know everything. You'll know how to do all your problems. So the first example: the voltage of a certain thermocouple as a function of the temperature is given by E equals 2.8 T plus 0.006 T squared. If the temperature is increasing at the rate of 1 degree Celsius per minute, how fast is the voltage increasing when T equals 100 degrees Celsius? All right. So E represents the voltage. T represents the temperature. Okay. All right. So let's just write this down. E is equal to 2.8 T plus 0.006 T squared. All right. So if the temperature is increasing at the rate of 1 degree Celsius per minute. So let's write down what that means. So that's the change in temperature. So that tells us that dt little t is equal to 1. And they want to know how fast is the voltage increasing. Okay, so how fast is the voltage increasing? The voltage is changing, right? So that's dE dt. That's what we're trying to find. See, if E is the voltage, then dE dt, that's the change in the voltage, and that's what we're looking for. And then they want to know this for when T is equal to 100 degrees Celsius. So all we have to do here is take the derivative of this thing with respect to time. So we get dE dt is equal to 2.8 dt dt, big T, little t, plus, let's see, what is that? 0.012, I believe. Let me double check. Make sure I get it right. Yep. T times d big T, d little t. All right, so there's our derivative. Okay, now what are we looking for? We want to know how fast is the voltage changing. This is what we're looking for. So remember this. This is what you're looking for. So for all the other variables, you have to have a number to plug in. Okay? So we've got to have a number for dt, dt, and t. And do we have that? Yes, we've got the 1 and we've got the 100 to plug in. So we get dE dt is equal to 2.8 times 1 plus 0.012 times 1 times 100. And so we get dE dt is equal to, and let's see, that comes out to 4 volts per minute. And that's your answer. So see, it's really that simple. And yes, this problem was an easy one because they gave you the equation. But the thing I want you to understand before we go to the next problem is, okay, you're going to have to find something. Okay, so identify what you're going to find, and then you've got to have numbers to plug in for everything else. It's just that simple. Okay? All right, let's look at the next one. It says the distance Q that an image is from a certain telescope lens in terms of P, the distance of the object from the lens, is given by Q equals 10P over P minus 10. If the object distance is increasing at the rate of 0.2 centimeters per second, how fast is the image distance changing when P equals 15 centimeters? Okay, so that, what that reads, it might confuse you a little bit. It says the distance Q that an image is from a certain telescope lens in terms of P, the distance of the object from the lens. Okay, so Q, the distance Q that an image is from a certain telescope lens, P, the distance of the object from the lens. Okay, so let me just draw a quick picture for you on this one. So if we have a lens here, let's just say you've got the lens right there, and we've got, let's say, here and here. So this is your object, okay, going this way. This is your image, okay. This is P, this is Q. All right. Now, look at this. So let's write down our equation. All right, it says if the object distance is increasing at the rate of 0.2 centimeters per second. So it says the object distance. So the object distance is P. That's this distance here. So we know dP dt is equal to 0.2 centimeters per second. And they want to know how fast is the image distance changing. Okay, so remember the image distance is Q. So that's going to be dQ dt. That's what we're looking for when P is equal to 15. Now this P right here, that should be a lowercase p. For some reason when I typed it up, it's capital. So, but this should be a lowercase p. All right, so all we do now is we take the derivative. Okay, so we wrote down all the information that they gave us. Okay, and so we've got dQ dt is equal to, now for this one, we've got to do what? We've got to use quotient rule. So quotient rule, the derivative of the numerator. So that's 10. Derivative of 10p is 10, but don't forget, times dp dt, okay, times the denominator, p minus 10. Okay, so this right here is the derivative of the numerator times the denominator minus the derivative of the denominator. So what's the derivative of p minus 10? That's just going to be dp dt times the numerator, 10p. And this is all over the denominator squared. Okay. All right, so, let's just, I guess we could go ahead and maybe clean this up a little bit. dQ dt is equal to, I don't know, how about 10p, let's see, how do we want to do this? 10 let's just leave it 10 times p minus 10 times dp dt minus 10p dp dt over p minus 10 squared. All right, so now if I wanted to, I could actually simplify this more if I wanted to. And actually, you know what? We don't really need to, but I think I am. I think I'm going to simplify this more because it'll give you, just more practice on actually finding, simplifying stuff like this. So let's just go ahead and simplify it. So that's going to be 10p dp dt. I'm distributing the 10 and the dp dt minus 100 dp dt minus 10p dp dt over p minus 10 squared. So the reason I did that, you see this, those cancel out. And so we're left with dq dt is equal to negative 100 dp dt over p minus 10 squared. All right, so now we're ready to plug everything in. So look at this. Let me take this and let's bring it down here. All right. So we've got dq dt is equal to negative 100. Now dp dt, we're going to plug in 0.2 times 0.2 over p. Well, what do they want us to plug in for p? 15. 15 minus 10, and that is squared. And what do we get? We get negative 0.8 centimeters per second. And so what does that mean? It means the image distance, because remember, that's Q is the image distance. So the image distance is decreasing at the rate of 0.8 centimeters per second. All right. All right, so let's move to the next problem. Okay, so the first two problems that we worked, those were nice. They gave us the equation. Let's look at this one. Notice there's no equation here. And actually the rest of the examples, there's no equation. We have to come up with them. All right, so it says a spherical balloon is being blown up such that its volume increases at the constant rate of 2 cubic feet per minute. Find the rate at which the radius is increasing when it is 3 feet. All right, so what are we dealing with? The volume of a sphere, right? It's telling us how the volume is increasing, and it wants to know how fast is the radius increasing. So what's our equation? Well, it's the volume of a sphere. And the volume of a sphere is 4/3 pi r cubed. All right, now let's write down all the information they give us. Let's write down what they want us to find. All right, so a spherical balloon is being blown up such that its volume increases at a constant rate of 2 cubic feet per minute. So that's the change in volume. So dV dt is equal to 2 cubic feet per minute. All right. Find the rate at which the radius is increasing. So they want to know the change in the radius. So we're looking for dr dt is what we're wanting to find. And that is when the radius is 3 feet. So that's when r equals 3. All right, so that's all the information they gave us. So now we take the derivative. So we've got dv dt is equal to, so this power rule, so that's going to be 4 pi r squared. And then don't forget times dr dt. Now, what do they want us to find? They want us to find dr dt. So let's solve for that. So I've got to get rid of this, so I'm dividing this to both sides, right? The 4 pi r squared. So that's going to give me dr dt is equal to 1 over 4 pi r squared times dv dt. Okay, see, we got to get rid of this. So it's kind of like I'm taking this whole thing and multiplying by the reciprocal. So you can see here it's going to cancel out, and then I'm left with the 1 over 4 pi r squared over here. All right. Now, let's see. Do we know what r is? Yeah. Do we know what dv dt is? Yeah, it's 2. And then that'll give us dr dt, what we're looking for. So dr dt is equal to 1 over 4 pi times 3 squared times 2. And that gives us 0.0177, and we're in feet and minutes. So that's feet per minute. So that's how fast the radius is increasing, 0.0177 feet per minute. Okay. All right, moving right along. Here we go to the next one. It says the force F of gravity of the Earth on a spacecraft varies inversely as the square of the distance r of the spacecraft from the center of the Earth. A particular spacecraft weighs, I spelled weighs wrong, weighs 4,500 newtons on the launch pad. F is equal to 45 newtons for r equals 6,370 kilometers. They're giving you the radius of the Earth in kilometers, and then the force is 4,500 newtons. Find the rate at which F changes later as the spacecraft moves away from the Earth at the rate of 12 kilometers per second, where r is equal to 8,500 kilometers. All right, so that's a lot of information there. So they give us a bunch of information. So and we've got to figure out what to do with it. So first thing we need to do is come up with our equation. So it says the force F of gravity of the Earth on a spacecraft varies inversely as the square of the distance r. Varies inversely, the force does. So that's F is equal to what? K over the radius squared. Remember that varies inversely, varies directly, varies jointly. You did that in algebra, okay? If it was varies directly, it would be K times R squared, okay? Now, let's look at this. If you recall from these types of problems like this varies inversely, what do we need to do? We need to know what K is. We need to figure out what K is. K is some number, it's a constant. Well, how do we do that? Well, that's this information right here. Okay? See, it's telling us that F is equal to 4,500 when R is 6,370. And see, we know F, we know R, and we can solve for K. So let's do that. So I've got 4,500 is equal to K over 6,370, and that's actually squared. So that's going to give us K is equal to, so we're going to multiply this to that, and that's going to be a huge number. We may have to Yeah, we're going to need to write this in, we'll write it in scientific notation. This is, and your calculator actually gives you the answer in scientific notation. So we'll write it as 11.83 times 10 to the 11th. Okay, so that's K. All right, that's K. So let's plug it in. So we've got F is equal to 11.83 times 10 to the 11th over R squared. All right. So now let's write down the information they give us, because see, we've got our equation now. We had to do a little more work to get this equation. Okay, I mean, this one up here, yes, we had to come up with the equation, but it was easy. It was just the volume of a sphere. But this one down here, it wasn't so hard coming up with this, but then remember, you've got to determine what K is. And now we have our equation. Now we're ready to take the derivative. But first, let's write down what they give us and what they want us to find, like we did in the previous problems. Okay. So let's see what it says. It says find the rate at which F changes. So we want to know what df dt is. That's what we're looking for. As the spacecraft moves away from the Earth at the rate of 12 kilometers per second. So that means that radius is changing. So that tells us that dr dt is equal to this 12 kilometers per second, and they want to know when r is equal to 8,500. So that's what we're looking for there. All right, so to take the derivative of this, let's first 0.83 times 10 to the 11th times r to the negative 2. Okay. So let's go ahead and find, whoop, what did I do? I'm sorry, I wrote this wrong. I'm looking at my calculator. That is not 11.83, that is 1.83. That should be 1.83. Sorry about that. I'm sure some of you might have caught it. Okay, so we got all that written down right now. All right, so let's take the derivative using the power rule, and that is 11. That's not quotation marks. So we get df dt is equal to, so negative 2 times 1.83, that's going to give us negative 3.66 times 10 to the 11th r to the negative 3, subtract 1, and then don't forget times dr dt. And so I get df dt is equal to negative 3.66 times 10 to the 11th over r cubed times dr dt. So there you go. That's your derivative. Okay. And now we can go ahead and plug everything in. See, we're looking for df dt. So we'll plug the 12 in for dr dt and the 8,500 in for r. So I've got df dt is equal to negative 3.66 times 10 to the 11th over 8,500 cubed times 12. And when we put all of that into the calculator, we get negative 7.2 newtons per second. Okay, so that means the gravitational force is decreasing at the rate of 7.2 newtons per second. Which, does that make sense? Well, yeah, we're getting further and further away from Earth, so the gravitational pull would be decreasing. Okay. All right, so last problem here. It says 2 cruise ships leave Vancouver, British Columbia at noon. Ship A travels west at 12 kilometers an hour before turning toward Alaska, and Ship B travels south at 16 kilometers per hour toward Seattle. How fast are they separating at 2 p.m.? All right, so for this one, let's draw a picture. We can draw a picture with this one. So we've got cruise ships. Here's Vancouver, and we've got one travels west, so that's this way, and one travels south, that's this way. Okay. And how fast are they separating? So whoop, moved the screen there, didn't I? So we're going to need a line here. See this right here, see if it's going this way and this way, that's how fast they're separating. That's this distance here. So let's just label this thing. We'll label it X, Y, and Z. Okay? And of course this is a right angle. So what's our equation? Well, it doesn't really tell us anything, but we do have a right triangle, don't we? What do we know about a right triangle? Well, we know that z squared is equal to x squared plus y squared, right? Pythagorean theorem. Okay. Now, let's look at the information that they give us and what they want us to find. So it says 2 cruise ships leave Vancouver, British Columbia at noon. Ship A travels west. Okay, so that's the ship traveling this way at 12 kilometers per hour. So what is that? That's the change in x, right? How fast it's going. So that's telling us that dx dt is equal to 12. And ship B travels south at 16 kilometers an hour. So that's traveling this way. So that is dy dt is equal to 16. And they want to know how fast are they separating at 2 p.m. All right, so how fast they're separating, that's the change in z, right? So the dz dt, that's what we're actually trying to find. Now, are we going to need some additional information in order to do this? Maybe. We might. But I tell you what we do. We wrote down everything we could get from the problem so far. I mean, there's some other things, and I'll show you. But let's just go ahead and take the derivative and see what we get. So we got 2z dz dt equals 2x dx dt plus 2y dy dt. Okay, take the derivative with respect to t. So you can see that I need dx, I've got dx dt, dy dt, so I've got something to plug into here and here, right? And I'm looking for dz dt, so I could just go ahead and divide everything by 2z. Okay, so how about we do that? Let's divide everything. I want to do that in a different color. So let's divide everything by 2z, and then that way we'll have dz dt by itself. All right, so that's going to be dz dt is equal to x over z times dx dt plus y over z. Let me make that z better. And dy dt. All right. Now, we've got dx dt, we've got dy dt, but look at this, we need x, y, and z also. So x would be the distance, y would be the distance, right? So let's see, here we've got x is equal to, let's see, what is x? That is going to be 2 times 12, which is 24, y is going to be 2 times 16, which is 32. And those are kilometers. Now, how in the world did I get x? Well, they wanted to know how fast is this changing at 2 p.m. So we left at noon. So 2 p.m. is 2 hours later, right? And so what's x? Well, that's a distance, right? X is a distance. And isn't distance equal to rate times time, the 2 hours? So it's the rate, 12 kilometers per hour, times the time, which is 2 hours, noon to 2, that's 24. Same thing for y. Now, they don't give us anything for z, do they? You see that? They don't tell us how fast that distance is changing. That's actually what we're trying to find. But look at this. If we know x is 24, we know y is 32. This is a right triangle, so z squared is equal to 24 squared plus 32 squared. And so z is just the square root of that, which that is 40 kilometers. And I don't know, let me type it. I don't know if it's a decimal or not. Let's say 24 squared plus 32 squared. Yeah, it's 40 exactly. There's no decimal. I didn't know if the book rounded it or not, but anyway. All right, so there we go. So now we have everything. So all we do is we plug everything into here. Okay. So we've got dz dt is equal to x, which is 24 over z, times dx dt, which is 12, plus y, which is 32 over z, which is 40, times dy dt, which is 16. And so I've got dz dt is equal to, and that is 20 kilometers per hour. That's how fast the distance is changing. So, you know, don't try to do all this stuff in your head. Write down everything they give you. Okay? Write it down. And look, an important thing is write down what you're wanting to find, and then well, I've got to have numbers for everything else to plug in. Okay? Now, these are 5 examples here. If you go to my YouTube channel and you search my channel, just type in related rates. I have a ton of more related rate videos. They're like a video with just a single problem, and it's the title kind of describes what the problem is. So go check those out if you need some more examples. Okay. But yeah, that's the video. I hope it helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see y'all in the next one. Later.